So hi everyone, welcome to the last session of the workshop. I'm Alex. I'm going to be talking you through our lesson on machine learning and using MapMiner. So before I kind of get into the coding, I just want to show you a little summary diagram overview of what we're going to be discussing today. So I'm going to be introducing a few packages that we've developed for doing machine learning of material science data sets. So the main one of these is called MapMiner, and it links data retrieval tools. I'll go into what that means in a minute, with methods for generating machine learnable descriptors, and also visualization packages, and then tying all of these together with machine learning packages, which we didn't develop these machine learning packages. They're kind of very well known. And these are things like scikit-learn. Okay, so I'm going to go back to my blank notebook. So I said that MapMiner kind of links these data retrieval tools. So it interfaces with a series of materials databases. So these are things like the Materials Project, Citrine, AFlow, and there's more. But it also includes over 30 data sets that have been taken from the published literature. And so these are data sets which are ready to be used straight away. And so we can actually look at what data sets are available in MapMiner by using this get available datasets function. So let's go ahead and import that. So it's from MapMiner, and then all of these data sets are in the datasets module. And then we can import get available datasets. And once we've imported this, it might take a second. We can then just run that function, get available datasets. And when we run it, it's scrolled me all the way down to the bottom. If I scroll up, this prints out a list of all the available datasets in MapMiner and a short description of what those datasets contain. So for example, we have this Boltztrap MP dataset here. This is the identifier. And you can see it contains effective mass and thermoelectric data of 8,000 compounds taken from the Materials Project. So let's come down. Let's find a data set that we can load. So I'm going to use the dielectric constant data set, and we're actually going to load that in. So we can do that in a new cell down here. And so to load data sets, we need to use the load dataset function. So that is accessible from MapMiner .datasets, and then we're going to import load dataset. So let's import that. And then we can load our dataset into a variable called df. If we type df equals load underscore dataset, and then our dataset name is called dielectric underscore constant. And we also need to add a little bit extra here. We're going to add data home equals open quotations dot. And that's just a quirk of CoCalc, which means that we have to download the data set to the current directory. So if we shift enter, you'll see here that it's fetching this dielectric constant data set. That's because we don't actually include all the data sets in MapMiner to kind of keep the repository size down. And instead we upload them all onto Figshare. And so the first time you ever try and load it, it will download it from the internet. So all the data sets that are available in MapMiner are pandas data frame objects. So we had a nice introduction to those earlier. Oh, I'll just increase my font size a little bit. Hopefully this will make it more visible. So yeah, we had a nice introduction to those earlier from Rachel. So you can think of these data frame objects like Excel spreadsheets, except for I'd say they're a lot more powerful than Excel spreadsheets. They make modifying and searching for your data much easier. So we can have a summary of what's available in this data set by using the head function. So if we type df.head and then scroll up a little bit, you can see we have a kind of spreadsheet here where we have columns along the top and then our rows along the side. So in our data frame, we have things like the material ID, which are the identifier number from Materials Project, the volume, the structure object, and then the dielectric constant information here. So this is E electronic and E total. So you can see that if there's many columns, you might actually have to scroll across in order to see them all. And sometimes actually, if there's too many columns, they'll kind of get summarized by an ellipsis. And so you can actually just print all the columns that are in there using the columns attribute. So that's df.columns. And here you can see this is a list of all the columns in the data set. One nice thing about data frame objects is they have a describe function, which gives us a summary of all the numerical data in the data set. So if we type df.describe, you can see here it gives us some statistics about all the different columns in the data set. So things like the min and max and the standard deviations. So you can index data frames in a similar way that you would index a dictionary. So for example, if you wanted to select a column, so let's say we want to select the band gap column, we can do df, open square brackets, band gap. And then if we shift enter, you can see here, we've got a list of all the band gaps for each row in our data set. And this is what's called a series object's been returned. We can actually call the values attribute of this, and this returns a NumPy array of these different values. So we can also index the data set on rows instead of columns. And for that, we use the iloc command. So that would be df.iloc, and then we put in a number here. So for example, 100 would give us the 100th row, or it's actually the 101th row. And then here you can see just a summary of all the properties associated with that row. So data frames are really nice because we can use these indexing tools to filter them really effectively. So let's say we wanted to filter our data set to only include those with a volume greater than 580. So the first thing we do is we create what's called a Boolean mask. And this is just a series of true or false. So let me show you. If we do df volume, that's going to select the volume data. And then we're going to ask for all of the volumes that are greater than or equal to 580. And here you can use any Python comparators when you're filtering the data frame in this way. And you can see that we get returned a list of false or true, depending on whether the volume matches this criteria. So what I'm going to do is I'm going to store this line in a variable called mask. So this is our Boolean mask. And then I'm going to index the data frame using that mask. And you can see when I do this that now there's only 4 rows and all of them have volumes above 580. So you can see we've got a lot of extra columns here. Once we've loaded a data set, we might realize that we don't want all of them. And so we can drop the columns that we don't want using the drop command. So for example, here, I'm going to create a new data frame called cleaned data frame. I'm going to put equals df.drop, and then I'm going to drop the n sites column and the space group column. And when we use the drop command like this, we have to specify whether we're dropping columns or rows. And to do that, we use the axis option. So here I'm going to put comma axis equals 1. So this means we're dropping columns, and if this was 0, that would mean we were dropping rows. So if I do that, and then let's have a look at our clean data frame here, cleaned data frame, and we can run the head command on that. You can see that now we've got a data frame missing the n sites and the space group columns. So the last thing I want to introduce to you, which again is really useful when you're doing data analysis, is the ability to create new columns. So much like you can use the Python comparator kind of functionality like equals or greater than equals to, you can also use the Python math operators as well. So these are things like plus, minus, and times. And so let's say we want to create a new column in this data frame. So let me scroll up and show you what we have in here. We've got the poly electronic, poly total, and these are the dielectric constants for polycrystalline samples, the total and electronic contributions. Let's say we wanted to get the contributions from just contributed from the ionic motion of the atoms. So we could create a new column in our data frame called polyionic. So we index the data frame for polyionic. This doesn't exist yet, but we're going to create it. And then into polyionic, we're going to add, we're going to calculate it based on the polytotal and the polyelectronic. So here we're going to say equals df polytotal minus df polyelectronic. And if we run that and then have a look at our data frame again, we can see if we scroll all the way across to the far most right, that we have a new column in our data set called polyionic. Okay, so that's just a very quick introduction into how you can manipulate pandas data frames. There's an exercise associated with this first lesson. If we go back to the files directory, and then if you navigate to this unit 1 exercises here, I'm going to give you all 10 minutes or so to have a go at employing some of these techniques that I've just introduced on some other data sets from MapMiner. So you've got 10 minutes. I'd say you can all have maybe 7 or so minutes to do it, and then I'll go through the answers for the remaining three minutes. Okay, I think I'll go through how I would have tackled some of these exercises then. So this first exercise wanted you to load and examine the Elastic Tensor 2015 dataset. And so we can do that, as is the hint here, using this load dataset function. So what we need to do here is just ask for the dataset using the identifier, and the identifier is just the name Elastic Tensor 2015. And so if we put the identifier in here and run this cell, this will download the dataset from the internet and then initialize it into this data frame variable. So we then wanted to find out the largest value of bulk modulus in the dataset, and the bulk modulus is given in this KVRH column. And so we can get that by running the describe function on the dataset. So if I just do df.describe, and then we come across to the KVRH, and the maximum value is given in this bottom-most row, and so the maximum value is this 435 there. In the second exercise, you are asked to filter the dataset based on a certain number of sites. So we can do that using the indexing behavior that I showed. So here we can do data frame. The first thing that we do is create a Boolean mask. So we make our mask like this. We then filter on the number of sites. So n sites is less than 20. And we create a new data set called filtered data frame equals, and then we index the data frame using the mask. So if we run this, that should only take a second. We can then look at the number of materials if we wanted, just using the len command. So we can say len filtered data frame, and that gives us 975. And we can get the mean number of sites using the mean command of pandas data frames. So we can say filter df, ask for the n sites column, and then call the mean function on that. And you can see here the mean number of sites is 8.55. And then the last exercise was to remove columns which are unnecessary for machine learning. And so this is a very common thing that you'll have to do. And again, we can do this using the drop function. So here we're asked to remove all the sites so that it only contains formula structure KVRH. So let's first of all see what the rest of the columns are. So you can see we've got material ID formula, all of these. So one thing that you could do would be to use the drop command. So you would type df.drop. We can put the things that we want to drop in here. So for example, material ID, n sites, and then etc. with all of these. And then you can do, you need to specify that we want to drop columns. So we ask for axis equals 1. So that's one way of dropping these sites. The other way is actually we can index, and this is a bit of cheeky because I didn't actually show you how to do this, but we can index the data frame just asking for the site for the columns that we want. So the columns that I asked you to get there were formula, structure, and KVRH. So here we could say, let's make a new function, a new variable called toKeep. We're going to make this a list of these 3 columns. So this is formula, structure, and KVRH. We can then index the data frame using this toKeep variable, like that. And you can see that now our data frame only has that columns. So this is a really useful way of filtering your data frame if it has a lot of columns to begin with. Okay, so I'm going to go back to the blank notebook that we created, and we're going to continue with the second lesson. So firstly, I just want to show you another image, another summary image of what we're going to be covering. So, maybe I'll have to zoom out a little bit just to show you for a second. So in this second section, I'm going to show you how we can generate machine learnable descriptors that we can then actually feed into machine learning algorithms. And so the idea here is that so far throughout this workshop, you've been using these material science primitives, we would call them. So these are things like composition objects, structure objects, band structures, and density of states. But the machine learning algorithms that we want to use, they don't understand these kind of objects. So instead, what we have to do is convert them into raw numerical features, or that the machine learning algorithm will actually understand and be able to learn from. And so a large part of MapMiner is implementing tools to do this conversion. And so I'm going to use some terminology here. We call the things that you learn in machine learning features. And you can think of these just as vectors of numbers. We call the process of turning compositions and these objects into features, featurization. And the classes in MapMiner that do this conversion, we call featurizers. Okay, so how do we use some of these featurizers? So let's make a new cell here. We need to first create an object that we can featurize. So let's, for example, use a composition object. So we're going to make a composition. So to do that, we import the composition class from PyMatGen. So we're going to type from PyMatGen import composition. We're going to create a new composition for iron oxide. So here we're going to type Fe2O3 is equal to composition, and then we're going to put Fe2O3 as our composition there. So this is a PyMatGen composition object. We can then featurize that using the MapMiner featurizers. So all of the featurizers in MapMiner are in the featurizers submodule. So we can import one by going to from MapMiner.featurizers. And then here we want to select a composition featurizer. So we type dot composition. And I'm going to demonstrate how to use the element fraction featurizer. So I'm going to type import element fraction. And we can initialize this featurizer in a typical way that you would initialize any class. So we're going to just call it EF, and we're going to say EF equals element fraction, and then parentheses like that. So one thing I'll note is that here you see I'm importing this composition featurizer. For other featurizers which are based on different PyMatGen objects, like structures, for example, they would be in a different module, so they would be in the structure module. Or if it's a band structure, that would be in the band structure module. So all the featurizers available in MapMiner implement the featurize function. And this does that conversion that I was telling you about before. It takes in a primitive object and gives out a vector of numbers. So let's use this featurizer that we've just initialized. I'm going to create a new variable called element fractions. And this is going to contain our features. And then into that, variable, I'm going to put the features using ef.featureize, and then we're going to give it our composition object. So if we examine what's in this variable, just by putting it in there and doing Shift Enter, you can see that it's basically a whole string of zeros and then a couple of other entries. We've got a 0.6 and a 0.4. So what does this all mean? Well, these featureizers also implement a function called feature labels, and this tells us the title of each of these features. So each of these numbers is a separate feature. So we can type ef.featureLabels, and you can see that each of these is a different element. So this class is called element fraction. You may have worked out that these numbers are the fraction of that element in the composition. So how can we verify this? So if we type element, so let's have a look at the 8th element, which we know is oxygen. So we're going to index our element fractions, which we just created to get the 8th one. So we'll type element fractions 7. I spelled that wrong. And you can see it gives us 0.6, or this means that oxygen makes up 60% of the composition. And we can verify that this is oxygen by using those feature labels that I just showed you. So we can type ef.featurelabels and then look at the 7th or the 8th one there, and you can see that corresponds to oxygen. Okay, so here I've just shown you how to generate features for one composition. In general, you're going to be dealing with data frames, and these data frames are going to be containing many different compositions simultaneously. The nice thing about these featureizers is that they have utility functions for generating features for a whole data frame of particular objects. And so all these featureizers implement the featureize data frame function. So let's try it using this element fraction featureizer. The first thing we're going to do is load a data set. So let's do that now. I'm going to import that load dataset function. In fact, I think everyone should already have it loaded, but I'll import it again in case. So from MapMiner.datasets, import load dataset. And then I'm going to import the Berkeley super hard training dataset. So I'm going to type df equals load dataset, Berkeley super hard underscore training. And then again, we need to tell it to install to the current directory. So for that, we're going to type data home equals and then dots like that. So that's downloading that data set now. Once that's done, we can just have a look at what's in our data set. So you can see we've got a formula column, bulk modulus, and if we come across, we have a composition column here. So this contains a composition object for each row in the data set. So now we can use this featureize data frame function, which I just mentioned, to generate these element fraction features for every row in the data set. So to do that, I'm going to type df equals ef.featureize data frame. So in each case, all the featureize data frame functions for every featureizer follows the same format. The first argument is the data frame that you want to featureize, and the second argument is the column which contains the object that you want to featureize. So here we're featureizing compositions, so we're going to give it the composition column, and we can just put composition in quotes like this. And you'll get a fancy progress bar, and that was really quick. If we look at our data frame again using the head function and Shift Enter, and then scroll across, you can see that now we have all of these elemental columns correspond to the fraction that that element makes up of the composition. So here you can see that I featureized the composition column. If, for example, you were featureizing structures rather than compositions, you would need to give the column which contains structures rather than compositions. So in this case, it would be the structure column. So there's one last special case of featureizers that I want to introduce, and those are conversion featureizers. So first, to show you why they're important, I'm going to load a different data set. So this data set is called phonon dielectric _MP. So I'm going to load that now. Load data set phonon _dielectric _MP. I'm going to tell it to download in the current directory. So that's data _home equals dot. It's going to download this, and then let's examine this data frame. So here you can see there's not many columns. We have a structure and we have a formula, but we don't have a composition column. So if we wanted to generate composition-based features, we would first need to generate a composition column that we can featureize. So you think, okay, the formula is very close to the composition. Why can't we use that? Well, you see the formula here is a string object. It's not a composition object. So what we want to do is actually convert this string into a composition object. And that's why I have these conversion featureizers, just to make this sort of procedure very simple. So I'm going to import the conversion featureizer that can do this, and it's very obviously named string to composition. So the conversion featureizers live in mapminer.featureizers.conversions. So I'm going to import that now from mapminer.featureizers.conversions, import string, capital S, to capital T, composition. We can initialize this featureizer like we would any other. So I'm going to call this one stc equals string to composition. And then we can featureize the data frame to do this conversion in the same way that we featureize the data frame to generate composition features. So we can type df equals stc.featureize data frame. The first argument is the data frame that we want to featureize. The second argument is the column, which contains the object that we want to featureize. And in this case, it is the formula. So it's the formula column. And if we do this, this is really quick. We can then look at our data frame and see, if we scroll all the way across to the end, that now we have an additional composition column. So that's a very quick introduction into generating features. There's an exercise for you all to do now where you'll be generating some composition features, some structural features, and also using these composition featureizers. So this is in the files, and it's called Unit 2 exercises here. So again, I'll give you 5 or 6 minutes to have a go at these, and then I'll go through the answers. So I just want to respond to a question which was asked in the Slack. And that is, how powerful are these weight fractional features that I just mentioned? So can they describe all kinds of properties, or do they perform well on target properties? So the thing which I definitely should have mentioned is that was just one example of one of the more basic features that we have implemented in MapMiner. MapMiner actually includes thousands of different features based on featureizing many different objects. There's a summary that you can see of all the different featureizers available in MapMiner. If you go onto, if you just search for MapMiner features or featureizers, there's a link to this table of featureizers here, which gives a summary of all the different featureizers that are available. So for example, under composition features, we have ones based on different element properties, such as the ionization potential of that element. We've got things based on the oxidation state. So for example, ionic radii and things like that. And as you can imagine, different features are going to be different, are going to be beneficial for different problems. So if you have something, if you have a property which is very dependent on anisotropy, then a compositional feature is probably not going to be very good. You'll need to have something which can encode structural information as well. And so you might want to use some of the structure featureizers that we have available. So these are things like the dimensionality, which will encode the dimensionality of your structure and things like that. So coming back to Oh yeah, and the last thing I should mention is that there's no real guaranteed way of working out in advance which features are going to be best. And so generally what you have to do is try out a whole host of different features and see which is working for you. And that's actually something that we'll come on to a little later. So let's return to these Unit 2 exercises. I asked you to load a data set to start with. This is actually a useful time to introduce this load data frame from JSON function. This is a very convenient way to load and save pandas data frame objects in JSON format. So you can see it's been loaded from utils.io. There's a load data frame from JSON, and there's also a dump data frame from to JSON, which saves it to file. So let's load it. So the first thing you were asked to do was use the conversion featureizers to convert a formula to PyMatGen composition. So here you need to fill in the blanks. So as I've mentioned, the first argument of these featureized data frame functions is your data frame, and the second argument is the column that we want to featureize. And in that case, it's the formula column we were told here. So we can put formula in there. We were then going to ask to put in some composition features. So here we're adding the element fraction features, and we want to add them to the composition column. So we can replace this with composition. And then in the last example, you're going to add some density features. And so again, the first argument is the data frame. And then now we want to put featureize the structure objects. So we can put the structure column here. And this might take a little bit longer, but it still should be pretty quick. Okay, so now we can go on to section 3. So in section 3, I'm going to demonstrate how you can actually use these features to do machine learning. So for this part of, let me just reopen my blank notebook. Here we go. So for this part of the exercise, we're going to be using a package called scikit-learn. So this is an open source Python package for machine learning. And we've really designed MapMiner to try and operate with scikit-learn as efficiently as possible. So what we're going to do is load a data set where I've already added a lot of features which you can use for machine learning. So here's one I prepared earlier. We're going to load this data frame using that load data frame from JSON function that I just mentioned. So that's present in, so we'll type from matminer.utils.io import load underscore data frame underscore from underscore JSON. And this data frame is present in the resources folder. So we can load that in by typing df equals load, I'm not going to say all the underscores, but load data frame from JSON. And then it's in parentheses, quotations, resources / elastic. And if you just type LA, it should tab complete. It doesn't want to. Let's, oh no, I've spelled elastic wrong. Elastic, here you go. And we can select the one which says featureized at the end. And if we shift enter on this cell, we can now have a look at what this data frame contains. So you can see it has the structure, the formula, this column, which is KVRH, which is the bulk modulus column. So that's going to be our target property and the thing we're trying to machine learn. It has the compositions, and then it has all the features which have been added. So these are called magpie features. These were added using the element property featureizer. And then we also, I think if you come all the way to the end, we have some density-based features. So we have the density, the volume per atom, and the packing fraction. So the first thing we need to do is separate our data set into the features that we'll use for machine learning and the target property. And each of these has to be based in separate variables, because if you have the target property in the same object as your features for machine learning, then it's going to be a very easy machine learning challenge because it will just learn directly from your target property. So first of all, we're going to select our target property and we're going to call it y. So we're going to say y is equal to df we're going to index the KVRH, so the bulk modulus column, and we're going to ask for the values. So this is just going to be a NumPy array object of the bulk modulus. Next, we're going to separate our machine learnable features into a variable called x. So we're going to say x is equal to, and then we're going to just drop all the columns that we don't want from this data set. So here we don't want structure, formula, KVRH, or composition. So let's type that out. It's going to be df.drop. We have a list here of structure, formula, composition, and KVRH. So you'll notice that we're only keeping these numerical columns because, as I said before, these machine learning algorithms don't know how to learn these structure and composition objects. And the last thing we need to do is select the axis that we want. And because we're selecting columns, we're going to ask for the first axis. So axis equals 1, sorry. And then we can see the features that we have in our x variable by just calling the x.columns attribute. So here you can see this is just a list of all these features that we saw before. So scikit-learn makes it very easy to use these generated features for training machine learning models. So in the interest of time, in this example, we're just going to try out a single machine learning model. But in practice, it's probably best, if you want to get good performance, to try multiple models and see which gives the best performance for your problem. So a very good starting model, which generally can give reasonable performance, is called the random forest approach. So this is an ensemble method, and we can use it by importing it from scikit-learn. So we type from sklearn.ensemble import random forest regressor, where R, F, and R are capitalized. And we will initialize this model into a variable called RF. So we'll say RF equals random forest regressor. And we're going to initialize it with this attribute of n estimators equals 100. So if we run this, that should run very quickly. So this n estimators attribute here, this is an example of a machine learning hyperparameter. So most machine learning models in scikit-learn will contain these hyperparameters, and these will affect the performance of the model, so how accurate the actual final machine learning model is. And so in order to obtain good performance, you not only need to try out different machine learning models, you also need to try out different hyperparameters as well. And similarly, there's no way to really know in advance which hyperparameters are going to be best for your problem. The only way to find out is to try different values and then compare the performance of your model between them. But here we're just going to use n estimators equals 100 because that's a fairly decent value to start with. So we can fit our features to our target property using the fit method. So this is actually going to do the machine learning. So we can type rf.fit. The first variable is our features. The second variable is our target property. And this might take a little bit of time. And you see our CPU shoots up for a second then, but now it's finished. So that's actually trained the full machine learning model. So what we want to do now is evaluate how well it's doing. And so fit trains the machine learning model. We can use the model to predict unseen values by using the predict function. So here we're going to store the predictions for all rows in our data set by typing ypred equals rf.predict, and then we're going to give it our features. So ypred now contains a list of our predictions. So this is the predicted bulk modulus with units of gigapascals. And we can see how close these predictions are to what they should be, to the actual true value, by calculating the error. So scikit-learn includes a few different functions for calculating the error of predictions. So we're going to use the mean squared error function here. So for that, we'll do from sklearn.metrics import mean squared error. And we'll calculate the mean squared error by typing MSE equals mean squared error, and we'll just give it the y values, which is the correct bulk modulus values, and then the predicted values, which is y pred. And we can then take the square root of this mean squared error. And to do that, I'm going to import NumPy, and I'm going to call it NP. This is just a shortcut. So now NumPy is aliased as NP. And I'm going to type NP dot square root, and then this MSE variable here. So you can see we've got a mean squared error of our model of 7.2, which looks very reasonable. But there's an issue here, and I think anybody that's familiar with or has done any machine learning before will know that we've kind of committed a cardinal sin. We've trained our model and then predicted its performance and evaluated its performance on exactly the same data set. And so this is not evaluating the actual predicted performance of the model. It's already seen every point before. And so we need to evaluate it in a more rigorous way. And to do that, we use a technique called cross-validation. And this will check that we're not overfitting our model to our input data. So in the cross-validation approach, we split the data into a number of splits, we'll say n splits. And in this case, we're going to choose 10 different partitions, each of these partitions containing roughly the same number of samples. We train on n-1 of the splits, and we call this the training set. And then we evaluate the model on the final split, which we didn't train on. So we then repeat this process n number of times so that each split is at some point used as the testing set. And then we calculate our final cross-validation. So this will give us a much more unbiased estimate of the performance of our model. And so there's a number of ways of splitting our data set into these different partitions. And here we're going to use what's called the k-fold approach. So k-fold just means this is effectively n folds. So we're going to import this approach by doing from sklearn.model_selection import k-fold, where k and f are capitalized. And then we're going to create this k-fold object as k-fold equals k-fold with the capitals n_splits equals 10. So here, this is the number of splits that I mentioned. And this effectively means that we'll be using 90% of our data for training and then 10% of our data for testing. So now what we can do is use the cross-val score function of sklearn to actually do this cross-validation score, this whole process that I just mentioned. So here we can do from sklearn.model_selection import cross_val_score. And here I will type scores equals cross-val score. The first argument is going to be our model. So this is RF. The second argument is going to be our features. The third argument is the target property. And then the final thing that we need to say, or not the final, sorry, the next thing we need to say is how it should score our predictions. And we're going to use the negative mean squared error. So here we type scoring equals neg_mean_squared_error. And the last thing we need to tell it is to use this cross-validation, this k-fold approach for actually splitting the data up. And so to do that, we say CV equals k-fold. So now I'm going to run this, shift enter. This is going to take a little bit of time because this function is automating that whole process that I just mentioned. It's split the data up. It's going to train a machine learning model on 90% of the data. It's going to predict the scores for the remaining 10% of the data, save the average of those scores, and then loop over so that each split is at some point used as the testing set. So you can imagine here we're training 10 different machine learning models. And so it's going to take a little bit longer than before. So we'll just wait for this to run. You can see that we're at 100% CPU capacity. Hopefully CoCalc stands up. Oh, so that's finished. And so this calculated the negative mean squared error. We actually want the root mean squared error. So to get that, we can type RMSE underscore scores is equal to, and we're just going to loop over using a list comprehension. So it's not necessarily for you to type this out, but I'll just type it here. So I'm going to ask for the square root of the absolute value of S for S in scores. This is going to loop over all the scores and take the square root of the absolute value. And then we want the average of all these scores. So we can say numpy.mean RMSE scores. So here we have 18.59. So you can see that our previous root mean squared error was 7.2. So we've actually gone up a significant amount. And that's kind of as we would expect. So this is really indicative of and showing a more reasonable estimation of our model's predictive performance. So there's another exercise where you use some of these techniques that I've just gone through. Again, this is in the Unit 3 exercises. I'll again give you 5 or 6 minutes to have a go at some of these exercises, and then I'll go through the answers. Okay, I'm going to go through the exercise answers now. So again, we're using this pre-prepared data frame, which contains the features already added in. And that was just because sometimes adding these features can take a little bit of time. So it's just to streamline the process a little. So we can run this cell just to load our data frame in. And then the first thing, we can just have a quick look. It's the same one that we were using in those last examples, but it has the structure, the dielectric, and all these MagPi features. So the first thing I asked you to do was to split this data set into target property and features. So here I said that the target property is this total dielectric column. And then the other features that we don't want are, so the other columns that we don't want are the structure and the composition. So we can select the target property just by indexing that directly. So we can type df and then just index on total dielectric. And then for our features, we just want to drop the columns which aren't features. And so that is structure and composition. So then we were going to train a random forest model on the data set. So here you were asked to train a random forest model with 150 estimators. So here we can set that hyperparameter. So that's n estimators equals 150. Then for fitting, our first variable is our target property. Is our features. And then the second variable is the target property. So that's x and y. And then we're going to predict on our features again. And again, as I've already said, that this is not the correct way of estimating model performance. And so that's finished. And then we can just use this cell to print out the mean squared error. So that's 1.7 in this case. And then lastly, we're going to evaluate the model using cross-validation. And this time we're going to use 5 splits. So 5 splits would mean that 20% of our data is used for testing, and then the remaining 80% is used for training. And so here we can say just k-fold n splits is equal to 5. And then for our cross-val score, we've got this whole string of arguments. The first one is our model, so that's random forest. The second one is our features, that's x. The third one is our target property. We have our scoring already filled in there. And lastly, we want to set this k a CV attribute to be our k-fold. And again, this might take a little second. The thing I'll say is the fewer number of splits that you have, generally the cheaper the process is, because you have to do fewer, you have to train fewer models, and each of your models gets trained on fewer samples as well. So we'll just wait for this to finish, and then we can calculate the mean squared error. And here you can see it's gone up by about 4 times. So it's 4.125. Okay, I'm going to start the last section, the last part of this session now. And so I'm just going to return back to this blank notebook. And in fact, I'm just going to show you one little image to introduce this last section. So now we're going to be using a new package which we've developed called MapMiner, which, as the name suggests, automates a lot of the stuff that you would normally do with MapMiner. And so the ultimate goal, I'd say, of MapMiner is effectively that you can input a data set and then get out a machine learning model that predicts your property without really having to do a lot of the manual tuning by hand. And so MapMiner automatically decorates your data set using the machine learnable features. It then picks out which of these features are going to be best for machine learning. Then it runs a piece of software called AutoML, which will automatically trial out a whole host of different machine learning models and hyperparameters and optimize the best one. And then it will return to you what we call a pipeline, which can automate this entire process. And so here you can see this is just summarized where we have this auto featureization, the cleaning, this feature reduction, and then this AutoML. So in this section, I'm going to switch back to my blank notebook. We're going to load a data set of dielectric constants. Then we're going to fit a pipeline to this data set, and then use this pipeline to predict materials properties. And then finally, we'll actually show you how you can investigate what this pipeline is actually doing under the hood and all the different steps involved. So the first thing I'm going to do is download or initialize the data set that we'll be using. Sorry, I said dielectric constants before. We're actually going to be using yield strength. So let's load this data set in. So we can do df equals load data set. And then this data set is called mapbench underscore steels. And again, we need to set data underscore home is equal to the current directory. So that's dot. So you'll see this data set is prefixed with mapbench. Alongside MapMiner, we've also released a set of benchmark data sets, which we've pre-cleaned and filtered to make sure that, first of all, the data is of good quality, and second of all, there are no duplicates or strange structures or strange values in there. And we're hoping that these data sets will find use as benchmark data sets if people are trying to evaluate new machine learning algorithms. So let's have a look what's in this data frame. We can type dataframe.head. And you can see that this is really pared down. We just have a composition column and a yield strength column, nothing else. So unlike some of these other materials, these other MapMiner data sets, which have the CIF volume already in there, these are kind of ready to go for machine learning, these MapBench data sets. So the first thing I want to do is just split up this overall data set into 2 parts. The first part is going to be a data frame that we'll be using for training, and then the second part is a data frame that we'll be using for testing. And this is similar to what these k-fold methods do internally, but it will just help us kind of demonstrate the process of how you would, first of all, train a model and then predict on unseen data. So I'm going to import from scikit-learn, sklearn.model underscore selection, import train test split, and then we can use this train test split just to split up our data set. So I'm going to type train underscore df test comma test underscore df equals train test split. I'm going to give it our data frame, and I'm going to tell it the test size. So this is in percentage of the overall data set size. So I'm going to say test size equals 0.2. So this is 20%. So if we run that, now let's have a look how many entries are in each of these data frames. So we've got our train data frame, which contains 249 entries. We've got a test data frame. Let's have a look at the length of that, which is only 63. So this is quite a small data set size. And that's just so that we can actually run this whole procedure in the time frame of the lesson. So our target property here is the yield strength. And so these were taken from an experimental literature search, and these values are in gigapascals. So we can, first thing we're going to do is just create a new variable called target, which is just the string of the column name. So we're going to say target equals yield strength, and there's a space there, no underscore. And then we're going to just drop this yield strength column from our train data frame, train data frame. And that's because, as we've already said, if you already have the target property in your training information, it's going to make the challenge very easy. So we can type test df equals test df dot drop. We can then just put target like this, and then axis equals 1. And if we do that, we can just check that now we only have this composition here. So this is how our data set needs to be in order for us to start using Auto MapMiner. You see, it doesn't have any other columns, no other features or anything else like that. Auto MapMiner is going to add all the features automatically. So Auto MapMiner is incredibly configurable. The main class of automating this entire procedure is called the matpipe class. So let's import that. So that's from Auto MapMiner, import matpipe, where P is capitalized. And we get a couple of warnings here, but those are safe to ignore. We're going to type pipe equals matpipe, and then we're going to initialize this matpipe from a preset. So if you wanted to, you could control every single configuration so that you had complete control over the full pipeline. But here we're just going to use one of these presets, which we've designed to kind of give general performance. So the preset that we're going to be using today is the express single preset. So I'm going to type this from preset, and then in quotes here, express single. So if you wanted to do general machine learning, I would say the express preset is a very good starting place. This underscore single just means that we're not actually going to be doing the automatic machine learning part. We're just going to train a single pipeline. And I'll explain a little bit more what that means in a second. So I just want to get started with this whole pipeline process. So I'm going to shift enter on this cell, and then I'm going to actually fit and start the matpipe process running. So to do that, we type pipe.fit. So you can see this kind of echoes the way you would interact with scikit-learn. Then the first argument here is our training data. And so this is going to be our composition, our data frame containing our composition. So that's train underscore df. And then the second argument is the column of the of our target property. So I'm going to type here, oh, I may have actually made a mistake just a little bit above here. Oh, yeah, sorry. So this is, okay, yeah. So I actually led you down the wrong way a little bit. So I've removed this yield strength from our test data frame. Our training data frame needs the yield strength column in there still. So we haven't actually done anything wrong. I think my words just didn't match my actions at that point. So let me just clarify this. So I'm going to just show the head of our train data frame and show you what's in there. So our train data frame contains the composition and the yield strength, and our test data frame contains just the composition. And so when we're fitting this pipe, we want to give it the training data frame with the composition and the target property, and Auto MapMiner will automatically remove the target property when it needs to. And so here we can fit this pipe by doing pipe.fit the train data frame, and then the target property. And this is just the string of the yield strength column. So let's run that. So you can see there's a log gets printed and we start seeing a lot of information. I'm just going to go down bit by bit. So you can see here, it's identified that the problem type is a regression problem. We don't have categorical data, otherwise it wouldn't be regression. The first thing that happens is this auto featureization. So it's working out which featureizers it can apply to our data set. It's noticed that we've got compositions and that they're in the composition column. And so it starts doing the composition featureizers, which it wants to. So MapMiner, we've selected a series of featureizers, which we found give very good performance. So the first thing it does is guesses the oxidation states here, because our compositions don't contain them. So this is one of these conversion featureizers that I already mentioned. And then you can see here, it skips the structure and the band structure featureizers because there's no band structures or structures present in our data frame. So it then goes on to actually generate all the features. So you can see the first features it generates are element property, then oxidation state features, electron affinity, ion property, leudemer, and yeah, those are all the features that it generates. You can see here it's skipping these band structures and other features. The next thing you can see is that it starts doing the data cleaning process. So it gives you a bit of information here. You can see here that it's replacing infinite values with NaN. It's handling the NaNs there. You can see that these 8 features were removed because they had more than 1% missing values. So these wouldn't have been very useful for machine learning. And then after the data cleaning is finished, it starts doing feature reduction. So we're starting with 249 features. Immediately, it removes 52 of these features because they have cross correlation of more than 0.95%. Sorry, more than 95%. And then it finishes doing the feature reductions. And you can see here, we're now going on to this single pipeline adapter. So this is what you see when we're running this express single preset. If you were just running the express preset, what would happen is this software called Teapot would start running. So Teapot is a library that does that uses genetic algorithms to optimize machine learning models. So what would happen is it would use genetic algorithms to trial out a whole host of different hyperparameters and work out which are best for your machine learning problem. So with Teapot, you generally give it an amount of time that you want to let it run. So I think the express preset is to let it run for 12 hours. So it would run for 12 hours, and at the end of that, it would give you back a model which it had optimized. But we don't have time for that today. So we're just using this single pipeline adapter, and this just uses a single machine learning model. And in this case, it's a random forest. And you can see here, it's returned and said it's successfully fit on our data frame. So a lot of stuff has happened. And normally you'd have to do each of these steps by hand, but you can see by using MapMiner, this is all automated for you. And so I think it can be a little bit overwhelming because a lot of stuff has happened, but actually you do have complete control over every step of this process. So if we just can scroll down to the bottom, a little bit of information is printed about this map pipe object here. I'll return to that in a second. The next thing I want to show you is how you could use this pipe object to actually predict some values. So what we can do here is use the predict function. So we're going to say test df equals pipe.predict and then give it our test data frame. So our test data frame just contains the compositions. Now what will happen is it will repeat this entire process, this entire pipeline that it's just created on our test data frame. So it will do all the featureizing that it needs to do, it will do the data cleaning, and then it will use the machine learning model which it trained to predict the target property. And we can examine the result of this by looking at the test data frame head function. And so you can see now it's added these feature columns. So these are the features that were actually used for machine learning. And if we scroll all the way across, you can see we have this new column here, yield strength predicted. So these are our predictions. So I've already shown you how you would evaluate this, how to evaluate the performance. I'm not going to go into that again. Instead, I just want to show you quickly how we can investigate what exactly has gone on other than just reading this log file. So to do that, I'm going to import this pprint command, which helps to pretty print dictionaries. So I'm going to import pprint, and then I'm going to generate the summary of this entire pipeline using the summarize function of the pipe object. So I'm going to type summary is equal to pipe.summarize, and then the other thing that we can do here is provide a file name. So I'm going to provide a file name and call it summary. And we can pretty print this summary by typing preprint.ppprint summary. So it's scrolled me down to the bottom. I'm just going to go to the top. You can see here that there's a section or a separate dictionary key for each aspect of this pipeline, which I walked you through before. So we have one on data cleaning, and it says exactly what happened. So it dropped none keys. If it had to, it would have done one hot encoding. It didn't need to in this case. You can see here the features that were generated. And you can also see, if we come down a little bit further, I think it's all just been cut off, but you can see that, yeah, you have basically a summary of all the different featureizers that were run. So this is a kind of short summary. There's even more of a full summary that we can generate by using the inspect function. So here I'm going to create a function, a variable called details. I'm going to type pipe.inspect, and I can ppprint this. And now this gives us even more information. So this now goes into exactly how all of the different interior kind of processes of this map pipe were initialized and how they performed and what the output was. So for example, it will give you all the information about the features that were removed due to having strong coherence with each other. So again, there's a lot of information that you can see. The last thing I just want to show you is that we can actually access all of this information programmatically as well. So we could, for example, have a look at what the best pipeline was at the end of the training. So in this case, we actually only had one pipeline, but if we'd done this AutoML, then we would have more. But to do this, we can type pipe.learner.best pipeline. And you can see here, it gives us that the best learner was this random forest model. And we can also, for example, look at what features were available, what featureizers we use, sorry. So we can type pipe.auto featureizer.featureizers and ask for the composition featureizers that were included. Okay, about 1 minute over time, but actually the one thing that I would like to mention is how we cope with persistence of these models. So let's say you ran this AutoML part of the code using Teapot and you let your code run for 24 hours. You want to be able to save that model so that you can come back and use it later, or maybe you want to send it to someone else to use as well. So this is all supported directly through these pipe objects using the save and load commands. So I'm going to create a file name variable here called, I'm just going to call it pipeline.p. And we can save this whole pipeline by typing pipe.save and then give it the file name. So that's been saved to the file. And then we could, let's say we start a new Jupyter notebook and we want to use this model that we've created. We can load that in by typing, let's call it pipe loaded is equal to matpipe.load, and then we give it the file name. And you can see it's just loaded it from file. And then we can use this pipe loaded in exactly the same way we would before. You can type pipe loaded.predict and then start predicting straight away. Okay, so that's everything that I wanted to introduce about AutoMapMiner. There's not really enough time to have an exercise on this, but I would just like to point you toward a repository that we have containing lots more notebooks on how to use MapMiner and Auto MapMiner. So it's called MapMiner examples. You should just be able to Google for it. So it's MapMiner_examples. And yeah, it's available on GitHub, and it contains a whole host of example notebooks for how to use these codes.